Hello everyone, my name is Ratchaneekorn Ammawan. I'm studying in telecommunication engineering at Suratnari University of Technology. Today, I'm going to talk to you about the modulation methods. My presentation is divided into two parts. First, I talk about meaning the modulation methods. After that, I talk about modulation benefits and application. Okay, let's get started. Modulation involves two waveforms, a modulating signal that represents the message and carrier wave that serves the particular application. A modulator systematically alters the carrier wave in correspondence with the variation of the modulating signal. The resulting moderate wave thereby carries the message information. We generally require that modulation be a reversible operation, so the message can be retrieved by the complementary process of demodulation. Figure 1.221 depicts a portion of an analog modulating signal part A and the corresponding moderate waveform obtained by varying the amplitude of a sinusoidal carrier wave part B. This is the familiar amplitude modulation AM, used for radio broadcasting and other applications. A message may also be impressed on a sinusoidal carrier by frequency modulation FM or phase modulation PM. All methods of sinusoidal carrier modulation are grouped under the heading of continuous wave CV modulation. Incidentally, you act as a CV modulator whenever you speak. The transmission of voice through air is accomplished by generating carrier tones in the vocal cords and modulating this tone with muscular action of the oral cavity. Thus, what the ear hears as speech is a moderate acoustic wave similar an AM signal. Most long-distance transmission systems employ CV modulation with a carrier frequency much higher than high-test frequency components of the modulating signal. The spectrum of moderate signal then consists of a band of frequency components clustered around the carrier frequency. Under these conditions, we say that CV modulation produces frequency translation in AM broadcasting. For example, the message spectrum typically runs from 100 Hz to 5 kHz. If the carrier frequency is 600 kHz, then the spectrum of a modulated carrier covers 595 to 605 kHz. Another modulation method, called pulse modulation, has a periodic chain of short pulse as a carrier wave. Figure 1.221c shows a waveform with pulse amplitude modulation PAM. Notice that this PAM wave consists of short sample extract from an analog signal at the top of figure. Sampling is an important signal processing technique and subject to certain conditions. It's possible to reconstruct and retire waveform from periodic samples. But pulse modulation by itself doesn't produce the frequency translation need for efficient signal transmission. From transmitter therefore combine pulse and CV modulation. Other modulation technique described shortly combine pulse modulation with coding. Modulation benefits and applications. The primary purpose of modulation in a communication system is to generate a moderate signal suit to characteristics of the transmission channel. Actually, there are several practical benefits and applications of modulation, briefly discussed to next page. Modulation of efficient transmission signal transmission over appreciable distance always involve a traveling electromagnetic wave, with or without a guiding medium. The efficiency of any particular transmission method depends upon the frequency of the signal being transmitted. By exploiting the frequency translation property of CV modulation, message information can be impressed on a carrier whose frequency has been selected for the desired transmission method. As a case in point, efficient line of sight radio propagation require antennas whose physical dimensions are at least 1 divided by 10 of signal wavelength. Unmodulated transmission of an audio signal containing frequency component down to 100 Hz would thus call for antennas some 300 km long. Moderate transmission at 100 kHz, as in FM broadcasting, allows a particle antenna size of about 1 meter. At frequency below 100 MHz, other propagation modes have better efficiency with reasonable antenna size. For reference purpose, Figure 1.222 shows those portions of the electromagnetic spectrum suited to signal transmission. The figure includes the free space, wavelength, frequency band designation, and typical transmission media and propagation modes. Also, indicate a representative application authorized by the U.S. Federal Communications Commission (FCC). It should be noted that throughout the spectrum, the FCC has authorized industrial, scientific, and medical ISM bands. Modulation to overcome hardware limitation. The design of a communication system may be constrained by the cost and availability of hardware. Hardware whose performance often depends upon the frequency involved. Modulation permits the designer to place a signal in some frequency length that avoid hardware limitations. A particular concern along this line is the question of fractional bandwidth, defined as absolute bandwidth divided by the center frequency. Hardware costs and complications are minimized if the fractional bandwidth is kept within 1 to 10%. Fractional bandwidth considerations account for the fact that modulation units are found in receivers as well as in transmitters. It likewise follows that signals with large bandwidth should be modulated on high-frequency carriers. Since information rate is proportional to bandwidth according to the Hartley channel law, we conclude that a high information rate requires a high carrier frequency. For instance, a 5 GHz microwave system can accommodate 10,000 times as much information in a given time interval as a 500 kHz radio channel. Going even higher in the electromagnetic spectrum, one optical laser beam has a bandwidth potential equivalent to 10 million TV channels. Modulation to reduce noise and interference, a brute force method for combating noise and interference, is to increase the signal power until it overwhelms the contaminations, but increasing power is costly and may damage equipment. One of the early transatlantic cable was apparently destroyed by high-voltage router in an effort to obtain a usable receive signal. Fortunately, FM and certain other types of modulation have the variable property of suppressing both noise and interference. This property is called wideband noise reduction because it requires the transmission bandwidth to be much greater than the bandwidth of modulating signal. Wideband modulation thus allows the designer to exchange decreased bandwidth for decreased signal power, a trade-off implied by the Hartley channel law. Note that the higher carrier frequency may be needed to accommodate wideband modulations. Modulation for frequency assignment. When you tune a radio or television set to a particular station, you are selecting one of many signals being received at that time. Since each station has a different assigned carrier frequency, the desired signal can be separated from the other by filtering. Where it's not for modulation, only one station could broadcast in a given area. Otherwise, two or more broadcasting stations would create a hopeless jumble of interference. Modulation for multiplexing. Multiplexing is the process of combining several signals for simultaneous transmission on one channel. Frequency division multiplexing (FDM) uses CV demodulation to put each signal on the different carrier frequency, and a bank of filters separate the signal at the destination. Time division multiplexing (TDM) uses power modulation to put samples of different signals in non-overlapping time slots. Back in figure 1.221c, show instead the gaps between pulses could be filled with samples from other signals. A switching circuit at the destination then separates the sample for signal reconstruction. Application of multiplexing include FM stereophonic broadcasting, cable TV, and long-distance telephone. A variation of multiplexing is multiple access (MA), whereas multiplexing involves a fixed assignment of the common communication results, such as frequency spectrum. At the local level, MA involves the remote sharing of the results. For example, code division multiple access (CDMA) assign a Unicode code to each digital cellular user, and the individual transmissions are separated by correlation between the codes of desired transmitting and receiving parties. Since CDMA allows different users to share the same frequency band simultaneously. It provides another way in increasing communication efficiency. In conclusion, I talk about the modulation methods. My main point was the primary purpose of modulation in a communication system is to generate a moderate signal suited to the characteristic of the transmission channel, and modulation benefits and applications. Actually, there are several practical benefits and applications of modulation. Briefly discussed 5 examples include modulation for efficient transmission, signal transmission, modulation to overcome hardware limitation, modulation to reduce noise and interference, modulation for frequency assignment, and modulation for multiplexing. Thank you for your listening. Do you have any question?